Uh, okay, can you see my talk? Let me turn on my
Yes.
pointer. Okay. So today's talk is about the predictive, all about predictive modeling in microbiology. So what we do and what has happened in the last few years, and what's the tools that's available for everyone to use. So first of all, let me share with you my objectives of this talk. A few points I want to briefly share what we are, who we are at the USDA, United States Department of Agriculture, and I talk about what is predictive microbiology and what's the use of it, who use it, and how you can be part of it without learning any scientific programming. So I think this is make everyone can join this research area easily. And then briefly talk about the USDA Integrated Pathogen Modeling Program. Okay, talking about the USDA. So this is the USDA organization chart. So you see, let me minimize my.
Yeah, that's a bar
Yeah.
at the end of the slide.
Yeah. Let me minimize it.
Okay.
So
Okay, now it's good.
if you see this USDA organization chart, is of course cabinet level. If you're in Malaysia, it will be a Ministry of Agriculture, but in in America, it is called the U.S. Department of Agriculture. There are many mission areas and many offices, but here we are under this called Research, Education, and Economics. This is our mission area, and if you within this mission area, it is the USDA it is under the leadership of Undersecretary of the unit of USDA. So research, education, and economics. So what we do is within this mission area, we do this way. We do research to create our research. Our whole mission of this mission area is to create a safe, sustainable, competitive U.S. food and fiber system. Try to bring strong communities together for families, for youth, and through this integrated research, analysis, and education. So we do every aspect of agricultural research. Of course, food, it is one of it. So under this REE, we call it REE mission area. REE, we have this agricultural research service. This is where we are, and then there are 5 agencies under this IE. USDA Agricultural Research Service is one of the premier. I think it's not one of the largest research organization in the world. We are top notch, intramural. Internally funded research organization within the USDA, and then we have 4 other agencies under REE: Economic Research Service, National Agriculture Statistics Service, National Institute of Food and Agriculture. This is for our extramural agency, and this agency is specifically designed to offer research grants to the university professors. And we also have the Office of Chief Scientist, but it is our internal arm. Our budget is about $2 billion US dollar, very small agency, but we are all over the United States, even internationally. So USDA Agricultural Research Service is divided into 5 regions. 5 areas. So we are in this northeast area, and then there are 5 different big areas. So in each state, almost every state of the United States, we have our office or research location there to support research. So under this USDA, we have 4 regional research centers. One is, of course, is us. Here we are in the Eastern Regional Research Center, and there's a Western Regional Research Center. This is in Albany, California. And Southern Regional Research Center is in Louisiana. And then there's Peoria, research center is in, I think they are called Bioproduct Utilization Research Center is in Illinois. So we are one of these four research centers were built almost at the same time, cost $1 million in 1930s, 1938. Now here we are. We have this Eastern Regional Research Center. If you come to us, now is actually the best time to visit our center. It's beautiful. The flowers are blossoming now, so very, very beautiful. We are here 86 since its foundation in 1938, and it's still operating. So within this Eastern Research Center, we have 4 research units. Each research unit, you can think about it, it's just like a university department. We have 4 departments here. If you look at if it is in a university, one of the research unit is called characterization and intervention of foodborne pathogens. This unit is specialized in molecular biology, detection of foodborne pathogens. And here he also has a small group for intervention research. My research unit, and Dr. Ahmed is doing the postdoc here. It's called Microbial and Chemical Food Safety Research Unit. Our research basically divided in these 2 areas generally, and majority of us is working on microbiology, food safety research, and specifically in this predictive microbiology. The chemical side of it, and we are developing the detection methods for like almost all kinds of foodborne contaminants, heavy metals, animal drugs, pesticides, environmental contaminants. We develop this methodology, and then we transfer the technology to our regulatory agencies to use, like FDA, and there's another under the USDA, there's another food safety regulatory agency called USDA Food Safety and Inspection Service, FSIS. So we will transfer our technology to them. They will use that to support their regulatory needs. Another research unit is about dairy and functional foods, and will support the U.S. Dairy industry. And then there's another unit called Sustainable Biofuel and Co-products research. And in the past, we have a lot of agricultural byproducts we want to utilize. So, and now this group is primarily working on this biofuel. So 4 research units in this building. And this building is actually the American Chemical Society landmark building. And we developed a food dehydration technology, and it makes mashed potato. Or if you go up to the market, if you see certain potato chips, like a Pringle brand, the technology originally was developed by our research center. Now, let me switch gear to talk about this predictive microbiology. I'm not sure if you have heard of this term, and it is quite a newer area of research in traditional food microbiology. If you studied about in 1980s and 90s, so it's an area of research that in food microbiology specifically, we are limit our scope in food microbiology that applies mathematical models to describe the fate of pathogenic and foodborne pathogenic and sporadic microorganisms in food, undergoing complex changes in environmental changes, such as temperature and other conditions like pH, water activity, and so on and so forth. So what supports this predictive microbiology? What to do this kind of predictive microbiology? We need to see these 3 predictive microbiology at the 3 pillars to support this research to continue. One is microbiology. We need to know food microorganisms, and also it has to be related to food. So we're specifically interested in how these foodborne pathogens or sporadic organisms can change in the food system. And of course, we need the strong background in applied mathematics. So within this predictive microbiology, there are generally two types of people or two general perspectives. One is end user. The end user is the person that uses the model. Who are they? They are using mostly in the industry or regulatory agencies or someone, even consumer. Like someone just want to use a model. Use a model that can make some prediction, okay, to see how long food can be put on the shelf and is it safe or not. Something that if from the end user, it's something that I can use, just make a prediction. And most the users are mainly in the industry and regulatory agencies. But we are here at the Eastern Region Research Center. We are in the developer side. We want to make model available for other people to use. So to do this, the model has to come from somewhere. So somebody has to perform this kinetic analysis to collect some data in the laboratory, and then identify a model as something they can use. And then in the meantime, we want to understand how bacteria microorganism will grow and survive. That means to understand some kinetics. And then we want to, from the experimental observations, we want to extract as much information as possible. This is called inverse analysis in a formal term. So we want to, from our growth curve or survival curve, we want to find out some fundamental information from this that can reflect this microorganism. And what we really need is systemic experimental design, data analysis, and computer programming to put a model together. So you need someone to develop models, or you can do it. So this is what my objective of this talk. I can show you that everybody can do it if you want to. Let's look at a very simple model. Everyone actually in food science, everyone knows. This is a thermal inactivation curve. Very simple. We put microorganisms under heating conditions, under constant temperature conditions, and so long as the temperature is high enough, would you see this linear curve? This is called, if kinetics term, this first order reaction. From this first order reaction, we can see from each curve, we can get a D value. And from a D value, all these different temperature conditions, we can get the effect of temperature on bacterial survival. And then we can calculate the Z value. These are two simple mathematical equations, and yet it is fundamental for modern food industry. Without this original research in this kinetic analysis, there will not be the canning industry will not be there. So because of this simple model, so we can calculate the lethality based on from time temperature history. We can do some calculation. This is the time temperature history, and then we can integrate over time to calculate the lethality based on this D value and Z value. So this is because of this very, very simple expression. It established the science of food. But thermal inactivation is kind of relatively easy. But when it comes to bacterial growth, it's a lot more difficult, because bacterial growth, even under constant temperature conditions, usually you will see this kind of curve as time goes. So the first phase, we call that lag phase. The bacterial microorganism will stay, the population will stay the same for a certain period of time, because it starts to, microorganisms start to divide. And then the bacterial goes into this exponential growth phase, and then goes into the stationary phase. And by the time it reaches stationary phase, food is usually beyond consumption. And in the end, there's a decline phase. Food is totally rotted. So this kind of expression mathematically has been challenging for many, many years. That's why the predictive microbiology started kind of late, in late 1980s and early 1990s. We start to, food microbiologists began to appreciate the computer programming and the mathematics and use that in food science. So now we can do some experiment, because this predictive microbiology, the methodology is kind of very, very mature now. So you can conduct experiment under different isosomal conditions. You can observe these growth curves, and one condition at a time. So T1, T2, T3, and you can see the temperature effect on bacterial growth. And then you can examine each one of them for this lag phase, exponential growth phase, and stationary phase. And in the end, as you can look at different shape of curves, some may not have a lag phase, but we have model for each of these conditions. So based on these individual observations, we try to find out how temperature effect on bacterial growth rate. So basically, each of these, we can plot it out and try to find out where the maximum growth temperature, where is the optimum growth temperature, and where the minimum growth temperature is for a microorganism. So it's before the modern food microbiology, and this is basically you have to rely on hand drawing to do the calculation. But now we have a quite material theory for it. So each one of them is reflected by the behavior of microorganisms. Each data point is reflected in the what we call the kinetic parameter of the microorganism. Then we try to divide historically, try to use mathematical terms to describe all these the models in predictive microbiology. Generally, in predictive microbiology, there are three different kinds of models we have. One is primary model, which is looking at under constant conditions, what this time of how time affects the growth or survival, just like a d-value. And from the growth curve or survival curve, we want to determine that is the survival curve is a primary model. And then the second type of model, we call it secondary model. It's the effect of different temperature conditions or other environmental conditions affect how these conditions affects bacterial growth and survival. So the model for this kind of curve, what we call it primary model. The model for this kind of curve, what we call it secondary model. So once the models are developed, we can combine primary and secondary model to make prediction. What we call it this treasury model. So it's the application of primary and secondary model for prediction. So the first two models, primary model and secondary model, is mostly in the domain of model developers, which is what we do at the USDA and what Lulu, Dr. Hamed is doing in the laboratory now. And that treasury model is that once the primary model and secondary model are developed, we can combine them and write a computer program, or in Excel, we can make prediction. So you can use as simple as an Excel spreadsheet, or some special computer program to do it. So this is in the domain, mostly in the users. Most people are interested in this model, this type of model. They don't really care about primary model and secondary model, but they want this type model to be useful for them, like the food industry. They want to predict the microbial shelf life, when food is going to expire, that kind of application. So let's look at this. Everybody knows, everyone knows in food science. So if you think about the tertiary model, is this methodology, integration. So the primary model is this one. The secondary model is the effect of temperature on this d-value. And after that, the accumulation and the cumulative lethality, sum of all small areas. So this is the temperature history, time temperature history of a microorganism. And then based on the d-value, we do this summation. This mathematically, we call it integration. Integrate this over, and then we can calculate pretty confidently. We can predict the safety of a CAM product or only thermally processed food product. And this is called tertiary model. Now, again, primary, secondary, and tertiary model. So what we do in the laboratory now, we want to find the best models they can describe bacterial growth and survival, and the best models they can describe the effect of the environmental conditions, mainly temperature, because once a food is formulated, the time and temperature are the main factor affecting the bacterial growth. And actually, it's the temperature, because time goes on, and the temperature of the environment will affect how long the food will spoil or expire. So our job in the laboratory is to estimate these parameters, a d-value or growth rate. And then we will split a lot of data to develop this secondary model. And then finally, we'll put things together to develop this a package for other people to use. And we do all three of them. So in the past, data analysis in predictive microbiology, using linear model as an example, is very easy. You can do it by hand. Now you can do it by computer. So for example, for this kind of curve, you don't really need the computer to do that. So you just need to get the experimental observation, and then you draw a curve, and then calculate the slope, and then you can do the easiest way. You do some linear regression. You can do that using Excel. You don't need really complicated tools, but you don't really need Excel. Actually, you just need to have you can do it by hand, a drawing paper and a pencil. You can calculate the d-value and z-value. But when it comes to this bacterial growth model, it is kind of complicated, because there are this lag phase, experimental phase, and stationary phase. Historically, when we are food scientists are not so good in mathematics, and this becomes a stumbling block for us for quite a while, because the canning industry was developed very early on, 100 years before, but we still for a while we did not have a good tool or methodology to analyze this kind of curve. Now, and then make things even a little bit more complicated is that, unlike the thermal inactivation, the z-values, it's basically a linear function of temperature. But for bacterial growth, the growth rate is affected by temperature in a more complex way. There's no easy model to describe this kind of relationship, and to accurately determine this maximum temperature and optimum temperature and minimum temperature. And you can do it, we can determine this mathematically. You can do it by hand, in the experiment. You can observe them, but you just do not have a good way to describe it mathematically. Okay, this kind of complex. Models in predictive microbiology, historically, we use empirical models, such as some model that look alike. As long this is in the early days. As long as we have a mathematical relationship, that kind of look like a growth curve, we will use them. So now we are more developed. We have semi-mechanistic models based on certain biological principles. We can now quite confidently describe the three phases of bacterial growth. So let's look at how this one can be done. So you can also, if you don't want to use a computer, that's okay too. You just need to have a pencil and a ruler, and you, of course, you have run do some experiment to measure this growth curve, how bacteria grow. You inoculate microorganism, and then you observe, and then you develop this in a curve. So you want to estimate the lag phase, you just need to draw two curves. So one is the horizontal curve, one is this tangential curve, and this intercept determines the lag phase. It's a traditional way of definition for this growth curve. And then you can draw another curve, and you can in the intercept between this top horizontal curve and then exponential growth phase, it determines this stationary phase. You can do it by hand too, but when you have a lot of growth curve, this kind of not convenient. Also, there's no real good mathematical model for it. We cannot use it easily in another situation. So this is just a simple expression. But this three curve methodology later on that led us into this more modern approach. But now the methodology behind this model development now we can confidently develop a continuous model. We do not need to these three segmented curves. We can do it. Use quite good mathematical models to describe the entire process. But the methodology behind this model development is called nonlinear regression. All primary growth curves are nonlinear, and almost all secondary curves are nonlinear. So for linear curve means that observation, you can use a simple linear curve for it, and we can do it easily using it by hand or using Excel. But for this nonlinear curve, it's a good model, a useful model. They can continuously describe this growth curve. It's kind of challenging historically, and people like receive enough education in higher education would rely on certain tools in graduate school or engineering school. They will usually use one of these tools to develop this to do this nonlinear regression. So of course, SAS, it's used by a lot of statisticians, but it's used in a lot of agriculture schools. They teach this SAS, and SAS is very capable. And also this Mathematica, also this SPSS, certain kind of tools. It's developed by IBM, and if you are in the engineering school, they will probably use this MATLAB. And all these are what we call it kind of expensive proprietary tools you have to pay or use. But there's another one called R now. R it's a statistical analysis tool, and it's very, very powerful, but it's free. So a lot of graduate schools now teach students how to use this R. We have these tools. We have a lot of mathematical models, but for a lot of food scientists, a lot of food microbiologists, we realize that all these commercial data analysis or free open source, free mathematical analysis tools, statistical analysis tools, they are very powerful, but all of them require some kind of learning in this program. You need to know how to use this programming. You need to program science, program R or mathematics. Otherwise, you will not be able to use the tools effectively. But all these tools now I described in the last slide are not user-friendly. They are quite difficult to use and need some training. Most are very expensive outside our university. And for us, we have to pay a lot of license fees to use this kind of software. And all these tools, because each model, each site uses different way of data analysis, it can lead to different variations in models, different way of expression. So but the nonlinear regression is particularly challenging even for skilled users, because nonlinear regression problem requires you some kind of understanding how this mathematical model works and the proper choice of initial value. Otherwise, the research, the data analysis will not go easily made up. I've seen people from other part of the world send me this data curve. They are perfectly okay, perfectly good, but they just don't get the result. And the reason is that the initial value were not properly chosen. So let me give you an example. Let's use this example, a very simple growth curve. And
Totally, Han, can you move the tab? Can you move the
tab.
zoom? Yeah, maybe you can move it down so we can see the title of the slide.
Oh, let me see. Let me see.
Yeah.
Okay, let me see. Okay, is it now?
No. Okay, now it's good. Now it's good, I guess.
It is
Yeah.
called. Let me read the title to you, because why I hear. Okay. Is it the rule now, right? Okay, it's gone now.
Yes.
Okay, it's good difficulty of nonlinear regression. So this is a very simple growth curve, three-phase growth curve. Initial inoculation is 2, and then this is 1 hour lag time, and then this is maximum growth concentration is 8 CFU, and the growth rate is 1 hour, 1 log per hour. This is very simple. We can see that easily by hand, by our naked eyes. But when you use the computer program to use it, and then using science program, and using a simple what we call a compass model, you may not get the result. The reason is that the nonlinear regression programming may fail, and the reason is the selection of the initial value. If you don't have a good don't choose the right initial value for the model, the regression will not go smoothly. And this is one example. And this fail 1, fail 2. Again, the choice of initial value. And fail 3, the choice of bad initial value. But this is mostly for this inexperienced data person who try to do this nonlinear regression using some sophisticated tools. And eventually, finally, it's successful when I use these 3 fails to demonstrate it is necessary for people to understand the science behind nonlinear regression and the proper choice of initial values in order to get meaningful results. So for predictive modeling, for most food scientists, particularly food microbiologists or food people major in food technology, there are a few challenges for us. Most people will think mathematics is too hard. Most people who are new to this predictive modeling, they will say, I don't know which model to use. So too many models, a lot of literature to read. And I don't know which model is better. So I don't know which one to choose. And then people will say, I don't have a program for it. So they can afford to have this advanced software tools. And then also, the most complaint that I heard in the past is that I don't know how to program. I just don't know. It's just very difficult for us to use. Okay. And there are additional challenges in the predictive modeling. So there are too many variations in the model. So if you look at it, literature from early on up to now, different groups would say their model is the best. So make other people to think which one to choose and how to select the best one. And because of this, the model's parameters may not be interchangeable, leading to inaccuracy. And the proper interpretation application model may become challenging. It is necessary to develop a standardized, a unified model that are used by everybody in terms of structure-wise. And also, everyone should be able to use the same language to talk to each other. Lag phase means lag phase. Growth rate means growth rate. So this is why we developed this IPMP, the Integrated Pattern Modeling Program. Pattern Modeling Program was developed in 2013, and in the process of upgrading that, develop a better version. It is based on a modern object-oriented computer language, and it has advanced scientific computing libraries, the same as those used in R, same as those in SAS and in MATLAB, but we just do it for free for other people to use. And then we also include the modern user interfaces so that you do not have to guess what to do, and it will visually help you go through the data analysis process easier. So we developed about 23, 24 models commonly used by people in the world, in the predictive microbiology community. So they know how many models, these models are useful for most of us. And you can directly compare. Let me put this one up. Okay, let me pull this one out. Let me see if I can turn this off. Let me pull this one. Okay. So let me just directly compare different models. You can, using the same set of data, you can use different models to analyze it. And it has been operating. This program has been operating since Windows Vista up to 11, and either in 32 bits and 64 bits computing system, you can use it interchangeably. So you don't have to install. It is compiled program. So you can go to, if you are interested, you can use Google search engine. It's just Google USDA IPMP, and it will direct you to our website and then tell you to how to install, how to download this program and use it. And there's no installation program. It is very easy to use. So when you open up the USDA IPMP, it is just like this. And I designed it. It is everything look like Excel. You know how to use Excel, you should be able to use this program. So it has this data entry area. So you can have growth curve, survival curve. You just enter it. If you have other tools like Excel, you've already entered the data in Excel. You can cut and paste, copy and paste the data into this data entry area, and then underneath data, this data entry area, there are four different types of models pre-designed for you. So you can pick and choose. You just look at the curve. For the data entry, once data is entered, it will automatically plot the data for you. And then after that, you just look at the data and how to, which one look like this kind of curve, and then choose from this, from one of the model. And then it will guide you through now very easily. So let me use an example for you. So, and everything just, you can drag, expand, and shrink these four areas can be manipulated easily. So let me use an example. So let's say you have a growth curve. This is a growth curve. Okay. So once you enter it, you click this is called submit data button. So the growth curve will automatically plot it out for you. So if you look at this curve, you think one other model called low deck space model, it could be used for this growth curve. You just pick and choose this curve, and then once you pick this curve, and an interface will pop up. So this what we call it the model select, the advantage of the nonlinear regression, of this IPMP over traditional nonlinear regression. It allows you to adjust the initial value. So this dots represents the raw curve or raw data. So once you choose a model, and the initial value will be plotted out for you. So it would there's a default value for these parameters. So you can adjust these parameters so that it's close to the look more closer to the raw data. This is what takes the initial guess value space away from the user. So you do not have to guess. You can visually inspect, look at the curve, and adjust the initial value so that the final curve, the initial selection, almost identical. It can be off, but close enough to your raw data. This will be this raw data, and this will be fine-tuned. So you can fine-tune it, and then you can use a slider, or this is a spin box to adjust the initial value. Once the curve is pretty much close, almost like the raw data, you can submit, create the submit model, and everything will be done for you automatically. So everything after that, the computation is done automatically. So all the statistics about this growth curve will be automatically calculated, and everything you need to know about the estimated value, and its standard error, t-value, p-value, upper and lower confidence intervals, and all these statistics about this model will be generated for you easily. So very, very quickly. And so basically, you just create the data, you ask you to do that, and then automatically generate the curve, and then adjust the initial values, and everything. This last step, create the model, and everything is done. So this one has been adjusted to the certain models. If you look at our curve, if you look at this raw data, okay, if you look at this raw data, is initial value of 2 log CFU. This is in log of 10. So, but keep in mind that mathematically now in predictive microbiology, electron log sometimes better for certain kind of model, and for certain model you can use log 10, of base 10. So if you look at this initial value of 2, so if it is natural log, it will be 4. And if it is this growth rate is 1, and in natural log should be 2.3. So let's look at our result. I'll present this using the simple curve. I'll show you. So y0 and y max predictive value. This is a low X phase model. Okay, it's let's see. Y max. Let's be. Oh, that's a different model. This is a different model. But anyhow, this is what we do. Initial value predict 2.3. Okay, the starting point is 3. It's not a 2. So what we do is 10. This is the everything is now calculated automatically. Yes, 1.1. Yes, 1. Final y max is 10, and here is 10, and y max is y0 is 3, and here's 2.9. So everything, this is the raw data, and this is the final data. This is the final data. So the curve has a different initial value. So anyhow, so everything is done automatically. So let me see. Okay, so let me do that. Oh, this okay. So this is the data curve. Yeah, that was confused. Originally it's 1.95, and then this is 4, and then the specific growth rate is 2.4. The growth rate originally is 1.05. So that's the original curve. So everything related to these results will be automatically generated for you. So within this IPMP, there are 4 different general models for you. One is the reduced model for growth curve that do not have 3 phases. And then the other one is full growth model. We have all 3 phases of growth curve. That phase, exponential growth phase, and the stationary phase. And then also we build into survival curves, and also build into the secondary models. So 4 different types of secondary models. Let me show you what they are. So a reduced model. So it's a growth curve that only has a typical growth curve has 3 phases. Next phase is exponential growth and stationary phase. But sometimes things happen in the laboratory, leading to incomplete observation. Sometimes you only have this lag phase or exponential phase, but you still want to extract information out from it. Also, growth curve that do not have growth the lag phase, you also want to extract information out of it. So for this kind of curve, there's no lag phase, and also growth curve that does not have this stationary phase with the reduced model is perfect for this kind of application. So we can do that. Also, you curves, most of the time we will like to see the full growth phase growth curve of 3 phases. So lag phase, exponential phase, stage phase, and full growth curve. There are 4 models built in. You can do it automatically using this one. And then there are survival curves. Of course, they are linear survival curves and different shape of whiteboard curve. And the IPMP build all these programs, all these 4 different types of model into this package, and then also look at the growth rate, effect of growth rate as effective effect of temperature on growth rate. So this kind of growth temperature range, the full temperature range, and also optimal temperature range, we build into 4 different types of model for you to use. You don't have to write a program. You just choose the model, create this secondary model, and choose the model, and everything is done behind the scene. So this is the example of growth curve, and we did it using IPMP to analyze this case. This kind of curve is no lag phase, and of course we have this 3 phase growth curve. We can analyze easily with this IPMP, and also the survival curves. Let me pull it down. Survival curves, different kind of survival curves and shape we can analyze easily. And so with this IPMP, one really very complex data analysis actually becomes a problem of data entry. So as long as you can enter the data into this IPMP, you know, you can look at the curve, you can choose which model to use, and then you take advantage of the graphical user interface to adjust initial parameters, because this is a critical step what we can to avoid the mistake of common nonlinear regression problems. So what's the initial guess value problems. So, and then all data analysis and calculation are done behind the scene, fast and very, very accurate. The program by itself is kind of very large, but once it is loaded to the computer, and everything is done easily. You can compare different problems for the same set of data. It's a game changer. You don't really need sophisticated tools now. Don't really learn programming, and you can do. Everyone can do. I encourage everyone to use it and learn it. There's some advantage of IPMP. we have unified model systems. Now everyone we have the same models to look at the same kind of model, same expression. So you can compare different parameters. You don't have to guess what the result of it, and making application a lot easier. The same model. So you can download it from our website. It is there. As long as you have the internet and to Google it, and it is compiled into a executable file. So you do not need to install. You can work from a jump drive if you want to. As long as you have data, as long as you have some need, as long as you want to have do some data analysis, it can be done easily. If you can use Excel, you should be able to use IPMP. So IPMP is basically developed for traditional predictive people want to work on predictive microbiology in a traditional way. So one curve at a time, you combine multiple conditions and to analyze each condition once at a time, and eventually going through the step by step and analyze the result. If you don't, this is a beginning. It's a beginning phase of data analysis, but we do have a more advanced tool now called because traditional predictive microbiology usually is a 3-step process. As I explained, you have to look at a lot of conditions using temperature as an example. If you need to collect isothermal observations multiple times, and then if you do analyze data, each one of them, and then you combine them to make this prediction. But the limitation of the traditional method, data analysis, is that every step you accumulate error. Every step, the error may be propagated to the next level, and the error of prediction can be difficult to estimate, or even sometimes impossible to estimate. So it's not a better way to do this, to extract information from this multiple isothermal experiments. Yes, we have this new tool, and based on this methodological global analysis. And if you combine all the data together and analyze primary data, and then choose a secondary model, and then analyze at the same time, and we skip this step-by-step process, we can do it. If you know the primary model, know the data, collect the data, know the primary model, choose the secondary model, and then search what we call a global analysis. We'll try to combine the best primary model and secondary model together, and to give you a result. So what we call a direct construction of treasury models. It has a large data. There's a certain advantage of it. It has a large data set. It tries to minimize the error globally. And it's a direct model construction. To direct construct a treasury model for you, and the model error can be easily estimated and interpreted, and the model is directly usable. So what we do, we explore this methodology a while back. So this is the data set we use to develop this global analysis, and eventually we came out with this developing tool. We started working on this algorithm in 2014. By 2016, the global analysis, what we call a one-step analysis, firmly established. And initially, the computational algorithm was implemented in SAS, but now we developed this IBMP global fit. Also, if you're interested, you just go to Google IBMP-global fit, and then this is the article that I published, and this is the same tool. Everything behind this IPMP global fit is based on this IPMP software tool that are originally developed. So if all the data if when you do that, you combine all the data together, and instead of looking at one curve at a time, you look at all the curves together. So different conditions together. And then you go to choose a primary model, and then choose the secondary model, and then everything is done automatically. And then it will give you this interface. Again, you just choose a model, and then the model parameters will show up, and then will ask you to adjust parameter. Once you look at the curves, they look close to each other, and then you just click the data analysis. Everything will be done. If everything is reasonably right, everything will be done for you automatically. And this is the model, the newest technology we have at this point. So everything the same, data generation, all the necessary statistics about this primary and secondary model will be automatically generated. You can use these parameters to make prediction right away. Okay, global fit. So this is a survival curve. This is survival curve. We can do survival curves for using global fit. This survival curve, and we can use growth curve. This global fit has been used in scientific publication. So this is a statistical audience in cooked potato and potato salad. So we can do it easily using this tool, global fit. So and at this point we have 3 products. IPMP global IPMP. It's called IPMP is traditional methodology for predictive microbiology, and then IPMP global fit. And then I just developed this IPMP dynamic prediction. Originally in 2017, I developed only have 1 model, but now has 23 models in there. So this is also built within this IPMP system. So this is Dr. Ahmed's work here. Bacillus cytotoxicus in liquid egg yolk, which she came here to work on a project, and we collect a lot of data, and then we publish it. Once the paper is published, and then we incorporate the model into this software tool. So behind that, you don't really need to know. Behind that is all the kinetic analysis, all the mathematical modelings. So what you need to do is to choose time. This is the time, and enter the time history of this product. This is called Bacillus cytotoxicus in liquid egg yolk. So how this temperature will affect this the growth of Bacillus cytotoxicus. So this it is using this example. The initial temperature is 4 degrees C, and within 2 hours it goes to 50 degrees C, and then will keep there for 3 hours, and then cool down. So how bacteria will grow? You click once the data is entered, you click this submit model, you choose a model, submit model, and everything is done here. It will calculate. So for the industry, I just need to know initial temperature, middle temperature, and final temperature, and how bacteria grow will be calculated. Everything automatically. And then this is summary report. So we just developed this product, and we are going to share it with USDA Food Safety Inspection Service, and then everything. I think this product, the product is ready to go. So we have compiled this product. In this program, we compiled 23 bottles. C perfringens. Dr. Hammer is working on the C perfringens now at this point. So we spent a lot of time in. Okay. All right. So this is the models included in this IPMP dynamic prediction. So this product, and basically you choose a product, choose time, enter time temperature history, and then you will make a prediction. So with that, so which IPMP global fit which you want to use depending on your purpose. If you have if you are a beginner, you can choose simple IPMP 2013. If you are using these more advanced, want to use more advanced data analysis, you choose global fit, and either one work for you. Okay. So we designed IPMP 2013 was designed with education in mind. We try to use that to train students how to engage in predictive microbiology research. But it has been used in scientific publications. There's been in more than 100 publications now, IPMP by itself. And we need, at this point, we need more students to be trained to work on predictive microbiology because it is an important area of research. But if you want to use confident, after you use IPMP 2013 and you become more confident in using predictive microbiology, then you can consider use IPMP Global Fit. And then after that, you can consider develop your own software tool. With that, I'd like to conclude my talk. Thank you very much. Thank you very much for your time.
Thank you very much, Dr. Lee Han Huang, for your great presentation. So I would like to welcome the participant to ask questions. You can either turn on your mic or you can write your question in the chat box. Right now, I have a question from a participant here asking about from Nurul Akila, what is the difference between IPMP 2013 and PMP?
PMP, okay. PMP, IPMP, there's two different applications. We're going to remember what I talked. One is end user. PMP is end user. It consists of traditional product. We studied from 1990s. We started from bronze, and then we call it bronze models. Originally called bronze models. So you have condition, you have pH, temperature. At that time, initially, basically, it's isothermal. So want to say I have E. coli in food. So I keep it in 2 degrees C, 30 degrees C. How long? I keep for 2 hours. How much bacteria will grow? You go to PMP for that. That is end user perspective. It's a software tool. And now, because originally was developed by the pioneers of predictive microbiology in our center, actually we developed this tool. So most users are, I think, regular agencies for industry. But initially, the models included in the PMP are bronze models. And bronze models may not be useful in food. So we expand that into solid foods, food models there now. So most of the IPMP models are isothermal. And they start to include some dynamic models now. But IPMP Global Fit is both. It's a real food, isothermal or dynamic. You can do that easily. I hope my presentation is not too boring for you.
Okay, thank you for the feedback. I have another question from. Oh, okay. Maybe I will, before I read the question, maybe I will allow a participant that want to ask like physically. You can turn on your mic and you can ask.
Yeah.
Yeah.
Can you hear me?
Yep.
Thank you, Dr. Huang, for a very interesting presentation, and it's such an honor for me to hear you live because I use your model.
Thank you.
Huang model for the primary model to feed my data. So I just want to make just to ask a question regarding the IPMP 2013 and also the global fit. So when you speak about the global fit, is it correct from my understanding that they will fit together at the same time for the primary and secondary models simultaneously? Is that?
Exactly. This is the purpose of it. The reason is that IPMP, because the science developed in phases. So beginning, we can only consider one condition at a time. So one growth curve at a time, and then analyze from one step at a time. So initial step, and we can for data collection step, and then you develop primary models, or call it primary model step, and then from the primary models, you have a lot of parameters. And then you combine that into secondary model. It's 2-step process. And when you come to application, another step, 3-step process, right? Primary model, secondary model, and then combining. So global fit is do everything at one time for you. because any analysis of primary models, you see a lot of error. And the error is not captured in the secondary model. Right? And then when the secondary going back to primary model to make prediction, you don't know how accurate the model really is. So it is the best way I know, there's no way to calculate that. But if you use global fit, all the primary data for primary model are combined together now. So put together and then against the secondary model. And then you try to minimize the error for the primary model. So to make the prediction error limited. So everything is captured. It's just like one snapshot. Take a picture, everything is there. You don't have to do two step or three step. And once that, everything is done for you. So you know, based on this global fit, you know how accurate your model can be. It's already defined. Everything is defined. So it is more advanced user. But for beginners, it's kind of more advanced concept. But we are way past the beginner step. We are into the global fit now. So global fit is the future for more advanced users, for primarily for more accurate prediction. And then you know the error is quantifiable. And then the reason we developed this one so that everybody can use it. Yeah. You do not have to pay for it. And you just go to our website, download, and use it. We built into this model, this software package, there's software instruction, tutorial, and also the example data set. You can use the data set against the software tool, and you can start working on it. And once you start working on it, you know how to use very easily. I haven't seen any people say negative about it. It's indeed very, very convenient. And
okay.
It's probably there's no programming at all.
Right.
After that.
That's very interesting. Dr. How can I ask another question still related to global fit?
Yes, please.
So it's mean for IPMP 2013, we have to start when we have the primary, then we get the lag phase or the growth rate, maximum growth rate density, MCD, and then we're going to use either one of it for the secondary models.
Yes.
For the global fit, when you see that it will done at the same time, one step, so they will capture all these parameter from the primary model at the same time?
Exactly.
Oh, okay, all right.
Exactly, everything. It becomes the tertiary model. What about its primary plus together? Yeah. So they are together. Once done, you can use the model directly. So I'm upgrading our 2013 because it's kind of 2013 kind of a while now. We want to upgrade that. And in the meantime, after that, my next project will be upgrade this global fit to include more models in there, model choices. Yeah, this is.
Okay.
Right. Thank you so much, Dr. Huang. Thank you, Dr. Howard.
Thank you. No
Sure. Okay, we have another question from the participant. From Siti Aimi Sarah. May I know the sample size that we should have? Like how many data needed to run the modeling?
Actually, this is a very interesting project. So a very interesting question. So let me use a linear regression as an example. Okay, to determine the growth rate, its growth rate is the linear part of the curve, right? So mathematically, high school, we need minimum three data points to determine the slope, right? So for the exponential growth rate, you need a minimum of 3 data points. Now, so next phase, you have the horizontal line. I will say at least 2 data points to establish this horizontal line, right? So the stationary phase, it's horizontal. And we usually get 3 data points, right? But because they are next phase, they are exponential phase, you will go up there. We know that it's a level, a horizontal, is a level line. So a minimum 2 data points. So 2 plus 3 plus 2. So how much? 7 data points for a full growth curve, minimum. To have a meaningful observation, right? So if you have only one data point in the experiential phase, I will be very skeptical because you don't know, it can go anywhere you do. But theoretically, you can use the 2 data points in the experiential phase, but you have to be very good. You cannot have any room in error. So 2 data points can determine a slope. That's true, but you better be very, very careful. You better be very, very good. Minimize all the experimental errors. But I would say 3, minimum of 3 for just for the experimental phase. So and then 2, 2, 3, 2, 2. So 7 data points. Of course, the more the better. But in reality, the more is not better. The more you waste your time. The more you create more error. So using minimum amount of data points, you get a better result. So I would say 2, 2, 2, 3, 2 for growth curve. Does it make sense to you?
Yeah, I hope so for the participant. I mean, yeah, you can turn on your mic if you want to make a comment on it later.
So I can share the screen again. So to show you this principle. If you want to, do you want me to share? Okay, let me share the screen. Okay, screen. Okay, share screen. So let me show this principle. So let me see the principle. Okay, use this one. This was too many data points actually, and that time we do not have enough experience. So okay, let me use this. Let me use this example. Okay.
Yeah.
So a full growth curve, right? Here is horizontal line. I have another curve. Actually, another it's to demonstrate. Another is. So this is this curve. Okay, use this as an example. So this is one. So theoretically, to determine this exponential growth rate, because it's the slope of this curve. So you need 2 data points, it's good enough. So one from here, you are knowing exactly where you are. Just 1 point and another point, draw a line. This is the exponential phase, you can determine it. And then here is 2 data points between this initial point to this lag phase, and 2 data points between this curve, this point to this point. So theoretically, you just need this 1, 2, 3, 4 to determine a perfect growth curve. But we don't know. Actually, when we see this experiment, we don't know where they are. So basically, I would say you need at least 3 data points for your experimental phase, and you can make a more confidently determine the growth rate. So 2 data points here, 3 data points in this experimental phase, and 2 data points in this stationary phase. You can confidently determine a growth curve, a growth model. So 7 data points minimum.
Okay, that's good. I have another question here from the chat, from Norlia. Can we use this model for mold growth?
Yes. As long as this model do not care mold, virus, or bacteria. It is population. As long as you have a population parameter related to population, you can use it. You can be how many colonies per gram, how many centimeters of growth in mold diameter. It doesn't matter, but the only thing it does is its data points, and then measure it.
Okay, that's good. I guess this is the last question in the chat. So from Rashidi, can we use IR and Raman data for your model?
The model is data blind. It looks at instrument blind. It doesn't care it's Raman, it is IR. All it sees is just data points. And then as long as data points fits the shape of the curve, it will analyze for you. And then it makes it easier because you can have freedom to choose initial guess. So you can visually see, what you see is what you are, what you get. So you see the data curve, you see the trend, you click the submit the data, it does everything for you. It just makes it's just like a Kodak long time ago there's a Kodak camera. And then you have a Kodak camera. You can just like anybody can pick and shoot, pick and point and shoot, right? And then the other one has Canon DSLR. It's very complicated. And then let me do comparison. And Canon or Nikon, the DSLR, you need very sophisticated, knowledge to manipulate the zoom and lens exposure time to get a perfect shot. If you get a Kodak or Fujifilm, those old traditional film or iPhone, you can point that, you can zoom, you click, that's it. This is the IPMP 2013 for you. Make sense to you? It is an analogy like that.
Okay, is there any more question from the participant? Okay,
Can I have
go
another
on.
one?
Yes, please.
Dr. Huang, what about model validation? What is the common practice in your laboratory? Are you going to do another set of data data generation, or we can use like calculation using bias or accuracy factor? Can you comment about it? Thank you.
Data validation. Okay, the data used in model generation is for model development. You cannot use for validation. So what we usually do is that to generate another set of conditions that's not used in the model development. So if the autosomal experiment, for example, every 10 degrees C, so 20, 30, 40, I will not use this condition, the data originally used for that part. So I will use 25, 35 in between, or at least to set aside a data set that's not used for model development. So this one is independent, truly independent. So it's not, not correlated. So for nonlinear regression or all regression analysis is the correlation of data affects accuracy. So you cannot do that. So we'll set aside of something that is, and then you usually will point us if there's anything wrong. We will know the data is not accurate.
Okay. Yeah. Is there any other question from the participants? Yeah, we still have times like about 8 minutes or so.
So any of you done this predictive capacity before? Using your own program, IPMP?
Yeah.
Yeah.
Go ahead, Dr. Juju.
I try several software, including your software, IPMP, but I haven't used the global fit, but I have an experience using the 2013 version. It's very useful, very user-friendly. Even though during my PhD, I didn't, because I did my PhD before you launched your software, is before 2013. So I use the other software. I use Sigma Plot, which is I need to add in each of the models inside the software, including yours. I use several, Compass, Logistic, and Barani as well. And Huang models, and then we do the comparison among the primary models. But then after I graduated, I saw the IPMP 2013 have been launched. So I've used that for my research currently. But it's good to know about the global fit, so we can see the primary and secondary model at the same time. As you keep mentioned, it will reduce the error using the model development. So yeah, it's very good.
Thank you for sharing.
Is there any other question from the participants? In the meantime, maybe all of you can turn on your camera because I would like to get this opportunity to have a photo session with our speaker.
Thank you.
Yeah. Can you turn on your camera? Okay. Yeah. Love to see some
Right.
familiar faces again.
This is 5 more months you're
Okay.
going back there.
Right.
So not down.
Yes, so okay, I guess okay. I'll have most of people. Okay, let me just take the photo now. So smile. 1, 2, 3. Okay, that's the first page. Let me first copy
All right.
here. And then the second page. Okay. 1, 2, 3. Okay, got it. So don't forget to fill in your attendance via the link provided. Okay, so is there any other question from the folks that joining today? Okay, if not, I guess I would like to thank Dr. Lee Han Huang for delivering your amazing talk, and hopefully all of us can benefit from it and try to use it. And I'm sure Dr. Lee Han can take a question even beyond this webinar, like after this by
Yes.
emailing him. And I'm sure you're also open for future collaboration with other folks if
Yes.
they are interested too, right? So
Okay.
maybe you
Yes.
can,
Yes.
tell us a bit about how to, and then what are the possible collaboration?
Possibly.
Yeah.
Okay. Okay. What happens is that they use Dr. Lulu Ham as an example. So when she graduated from Michigan State University, and somebody from your university contacted our USDA international office and wanted to send her over to USDA for additional training. But at that time was a peak of the pandemic. There was no way for me to accept any international students, visitors at that time. But since happened, I got a grant from our sister agency. So and I remember Dr. Lulu's Hammer's the qualification. So I was looking for someone to conduct the research. So I wrote to her, and she's agreed to come. So so that was history. So international student ARS is the international. We have international responsibility. We collaborate with people, with scientists from around the world. So if you are interested in to coming to developing coming to our laboratory, please write to me. If we have see mutual benefits, our research program and your research program, and then I train students from other countries to because really really hope that people from different parts of the world can build up this capacity in predictive microbiology. We have a lot of expertise in detection. We have not expertise in processing, but in technology, food science technology, but we have very limited expertise around the world in predictive modeling because it's methophobia. A lot of people may think mathematical models too tough and beyond, and also the predictive modeling too hard. In our laboratory, we do original research in modeling. If you want to develop program skill, we can train you. So because now food safety is the international concern. It's not just one country, US country. It's all over the world, the problem of the entire world. So we want to keep our food safe, and predictive microbiology is just one tool that we can use. So I accommodate as long as there's opportunity. I welcome visitors to my laboratory. So I think we are pretty established laboratory, so pretty good laboratory. So it's good training for a lot of international visitors.
Yeah, it is. And that's one way, which is a physical visit, right? But you can also do a non-funded agreement, right?
Yes, non-funded agreement. The non-funded agreement is an agreement between two entities, between the ARS and another agency. That means there's no fund exchanging fund, non-funded, because you are responsible for your part. That what we do is provide opportunity in our laboratory to do research for you. So that can be done too. So that can be done.
Yeah. Okay. Yeah, I'm sure that maybe once I go back, you are always welcome to come to Malaysia, especially
Thank
UPM,
you.
and also maybe touring to other university if you would like. So yeah, hopefully our collaboration will be happening in future as well with
Yes.
other universities in
No.
Malaysia. So yeah,
Thank you very
thank you so much, Dr. Lee Han
Thank you
Huang,
so
and
much.
all of the participants who are joining today. Thank you so much, and have a good day ahead. Assalamualaikum warahmatullahi wabarakatuh.
Bye bye now.
Okay.
Good job.